Hello and welcome, and thank you for joining me. In this video we're going to take a look at the experiment to measure the specific latent heat of fusion of ice. This is a very important experiment on the Leaving Cert Physics course, and it appears on exam papers quite regularly. Now, after watching this video, you should be able to do the following. You should be able to draw a label diagram of the equipment used in the experiment. You should know what measurements have been taken and what instruments are used to make those measurements. You should be able to write down the formula and do calculations using that formula. And you should know at least 5 different precautions to make the final result of the experiment more accurate. At the end, we will look at one of these questions, either the 2019 or the 2008 Honours Leaving Cert question on this topic. But before we look at the experiment itself, it is very important to know and understand the following 2 definitions. Now, we're all familiar with the 3 states of matter: solid, liquid, and gas. And we all know that to convert a substance from one state to another state, we have to supply energy. Energy has to be supplied. And this energy that causes a change of state is known as latent heat. And here is its definition. Latent heat is the energy or the heat needed to cause a change of state without a change of temperature. This definition needs to be learned, as it is a very, very, very important definition. And it's very important to note that during a change of state, when latent heat is supplied, there is no change of temperature involved in the substance that is under investigation. The second definition we have to be familiar with is that of the specific latent heat of fusion of ice. This is the energy needed to change the state of 1 kilogram of ice from its solid state to its liquid state without causing a change of temperature. In simple terms, it's simply the amount of energy needed to convert 1 kilogram of ice into 1 kilogram of liquid at the same temperature. It is very important to remember that in this context, fusion simply means melting. It has no relationship with nuclear fusion. So the specific latent heat of fusion of ice is a definition that we need to learn. It is the energy or the heat needed to change the state of a kilogram of ice from solid to liquid without causing a change of temperature, and it's this value, it's a value for this thing that we are seeking in our experiment. Now, moving on to the experiment itself, and in reality this is a particularly easy experiment to carry out. We get a copper calorimeter and we half fill it with warm water. We know the mass of the calorimeter and the mass of the water using our electronic balance. We know the temperature of the water and the calorimeter using our thermometer. We get 3 or 4 cubes of crushed, dried, melting ice. And each of those words have meaning, and we'll see what they all mean in a few minutes' time. We take our 3 cubes of crushed, dried, melting ice and we add it to the warm water. Now an energy transaction takes place, and in this energy transaction, the ice gains energy from the warm water. And we say the energy gained by the ice will equal the energy lost by the water plus the energy lost by the calorimeter. And from this equation, we can work out the specific latent heat of fusion of ice. We assume that the surroundings do not gain energy. There is no energy lost to the surroundings. And we minimize the energy lost to the surroundings by using cotton wool or polystyrene foam as lagging around the copper calorimeter. And we also put a lid on the calorimeter to prevent heat loss to the surroundings. We also minimize heat loss from the water by using a thermometer of low heat capacity, and that simply means it doesn't take much heat from the water when it's measuring its temperature. Moving on to the formula. And as we said earlier, in any heat experiment, the energy gained by something will always equal the energy lost by something else. And in this case, it's the energy gained by the ice, which will equal the energy lost by the water plus the energy lost by the calorimeter. There's an energy transaction. The ice gains energy and melts. These things lose the energy. In essence, they supply the energy in order to melt the ice. Now, putting formulas on this is easy enough, because the energy lost by the water can be calculated from multiplying the mass of the water by its specific heat capacity by the change of temperature of the water. And the energy lost by the calorimeter can be found by using exactly the same equation applied to the calorimeter, the mass of the calorimeter, the specific heat capacity of the calorimeter, which is usually copper, multiplied by the change of temperature of the calorimeter. By multiplying these three things, we get the energy lost by the water, and in this part of the formula, we get the energy lost by the calorimeter. It's important to note that these two values, the rise in temperature, or the drop in temperature of the water and the drop in temperature of the calorimeter, the change in temperature of each will be the same. Now, on the other side of the equation, the energy gained by the ice is easy enough to work out as well, because the first amount of energy, the first thing the ice does is it melts. It absorbs latent heat in order to melt from the warm water. And we can calculate this amount of latent heat by multiplying the mass of the ice by the specific latent heat of fusion of ice. It's very important to remember that this is the guy that we're trying to work out. We're trying to measure a value for that in this experiment. And after the ice has melted, it is now water at 0 degrees. And that will pick up a little bit more energy from the warm water. So it's very important to remember the ice gains energy in order to melt, but it also gains more energy after melting because it's now water, which rises in temperature a little bit more. And this can be calculated from the mass of the ice. It's now melted, so the specific heat capacity of water multiplied by the change in temperature of the ice. We always use this formula when there's no change of state, and we use this formula when there is a change of state. So this formula you will have to learn and you will have to memorize, because anytime a question on this topic comes up, they will clearly ask you to use this formula. So the energy lost by the water plus the energy lost by the calorimeter will equal the energy lost by the ice in order to melt, and that, of course, energy, as we said earlier, is known as latent heat. And after melting, the ice gains a little bit more energy, and this is the energy gained by the ice after it has melted. This formula, we will see how it is used shortly in a question, but it's your job to go and actually memorize it. And it's also important to remember that it's this value, a value for this here, the specific latent heat of fusion of ice, that is what we are seeking to measure in this experiment. In the experiment, we can measure the mass of the calorimeter and the mass of the water using an electronic balance. The constant specific heat capacity of water and specific capacity of calorimeter will have to be given to us. The change in temperature of the water, the change in temperature of the calorimeter are measured using our thermometer. We are assuming, because the ice is melting, that it starts at 0 degrees Celsius, so the change in temperature of the ice can be determined. The mass of the ice is usually determined at the end of the experiment, because you measure the mass of the calorimeter plus its contents at the end, and subtract from that the mass of the calorimeter plus its contents at the start. And after all that, the only unknown we should have is that value there, and we should be able to work it out. And here's another view of that formula. And as I've said earlier, the whole purpose of this experiment is to measure a value for the specific latent heat of fusion of ice. Everything else in the experiment can be measured and determined in the experiment, and the constants, obviously specific capacity of copper and water, will be given to us. I'm not going to dwell too much on the method and how to carry out this experiment, because you should have done this in your physics class anyway. The whole point of the method is to determine the values to be put into the formula that we saw earlier. So we measure the mass of the calorimeter using the electronic balance. We half or 2/3 fill it with warm water. We find the mass again, and by subtraction we have the mass of the warm water. We note the initial temperature of the water and the calorimeter using the thermometer, and we add 3 cubes of our crushed, dried, melting ice. We stir with the thermometer until all the ice has melted. We then note the lowest temperature reached. We, at the end of the experiment, find the mass of the calorimeter plus water plus melted ice again, subtract that from the mass of the calorimeter plus water at the start, and that's the mass of the ice used. Because that is actually quite often and quite frequently asked in the Leaving Cert, I'm going to just highlight that there again. That is how the mass of the ice is determined. Then by putting all our measured figures into that equation, as we've seen earlier, we should be able to work out the specific latent heat of fusion of ice. We'll look at an exact example from a Leaving Cert paper shortly. Now, as in all these heat experiments, there are some precautions you can take to make the final result more accurate. These are very, very important to remember. They are so common that students tend to get sick of them, but they're very, very important to go through and memorize. Obviously, we prevent heat loss to the surroundings by lagging the calorimeter and always give a named insulator that you can put around the calorimeter, like cotton wool or polystyrene foam. We can put a lid on the calorimeter, as that will also minimize heat loss to the surroundings, heat loss to the air. We always use a thermometer with a low heat capacity. That means to minimize the heat absorbed from the water. It's always good to use a more sensitive thermometer. What does sensitive mean? It means it measures to more places of decimal. Better still, we can use a digital thermometer, which is usually more sensitive as it measures to several places of decimal. One thing the students can say is, you can say polish the calorimeter, as this will reduce heat losses due to radiation. Minimal, but it works in theory. Now, there's some little precautions that are very unique to this experiment and need to be understood. The first thing is we crush the ice so it will have greater surface area, so it will melt faster. Okay, and we want in a heat experiment to carry out the experiment as quickly as practically possible in order to minimize heat loss to the surroundings, or heat gain to the surroundings in some cases. So crush the ice so it will melt faster because it will have a higher surface area. In our experiment, we assume in the formula that the ice is melting. How do we know that its temperature is at 0 degrees? Well, if the ice is melting, we know its temperature is at 0. An incredibly important precaution is this one here, and this is one that you really need to focus on. The ice has to be dried ice. It has to be dried with a tissue paper or some sort of cloth in order to make sure that only ice is added to the calorimeter. If we add water to the calorimeter, if up here in our experiment we have a layer of water around the ice and we add that wet ice, as it's known, into the calorimeter, the layer of water has already changed state, so it cannot again absorb latent heat from the calorimeter. So it's very important that the ice you add is physically dry. It is dry, it is pure ice, there's no layer of water around it, and that means that it can absorb latent heat. It hasn't already changed state. Now here's a list of questions that I think could be asked in a Leaving Cert exam. Why is warm water used? Remember, ice will melt in cold water but will just take longer. Why is warm water used? So that the ice will melt faster. Why was the ice crushed? Well, crushed ice will have a larger surface area, and that will also mean it will melt quicker, it will melt faster. Why was the ice dried? Why was any layer of water removed from the ice before we added it to the calorimeter? Well, wet ice, which has a layer of water around it, has already changed state, and the whole purpose of this experiment is for the ice to change state when you add it to the calorimeter and absorb latent heat and change state. So wet ice, water, cannot change state. It cannot absorb latent heat from the warm water. That is incredibly important to understand and learn. Why would it be more accurate if room temperature was kind of midway between the temperature of the warm water and the temperature of the final mixture of water and ice? If this was the case, then the heat lost to the surroundings from the warm water and calorimeter before you add the ice would be approximately equal to the heat gained from the surroundings after you add the ice. That is one that's asked quite a lot in several of these heat experiments, and it might be a good idea to memorize that. Heat lost to the surroundings is approximately equal to heat gained from the surroundings if the room temperature was halfway between the initial temperature and the final temperature of the calorimeter. Why was melting ice used? Well, melting ice we know to be at 0 degrees Celsius by definition, and we want our ice to be at 0. So why was melting ice used? So that we would know its initial temperature was 0. How would you make sure the ice was at 0 degrees? Well, one way you could do that is leave the ice soak in tap water for a few minutes before the start of the experiment. Why could using a very large mass of water in the calorimeter and using the same mass of ice lead to a less accurate result in the experiment? Well, can you imagine if you used a huge amount of warm water and a very small amount of ice, then very, very little ice would melt and the drop in temperature of the warm water would be quite low. This could result in a very small change in temperature of the water, and this would of course increase your percentage error, because the smaller the number you put into a formula, the larger this thing called percentage error is. Also has been asked several times in Leaving Cert, how was the mass of the ice found? Well, it's very simple. The mass of the calorimeter plus warm water at the start was subtracted from the mass of the calorimeter plus warm water at the end of the experiment, and the difference between the two would clearly be the mass of the melting ice. You could just add on as well, this is done with an electronic balance. And the largest source of error in this experiment will always be the smallest value, which in this case will be the mass of the ice melted. When we look at a Leaving Cert question in 2 minutes, we will find that the mass of ice is actually the smallest value put into the formula, and if you get that wrong, your percentage errors will be quite large. So the larger the mass of the ice, the better in this experiment. The larger the mass of the ice that you melt in the warm water, the better, as this will reduce the percentage error. And I think now what we will do is have a quick look at a Leaving Cert question on this topic. Before we take a look at the 2019 Ard-Teach Sort Level Honours Leaving Cert question, the most common question that students would ask at this stage is, should we leave our mass values in grams or should we convert them to kilograms? Now, you are never wrong if you convert mass to kilograms, but in this particular formula there are 4 parts. 1, 2, 3, 4. And you notice that each part of the formula has mass in it. So in this case, we can actually just be consistent and leave our values for mass in grams. Students usually find this easier to do and more manageable, and it will all work out in the end. So it's a little unorthodox, but it does work, and that's the way the majority of students actually do it in the Leaving Cert papers. So, in summary, you are never wrong if you convert to kilograms, but in these experiments, these latent heat experiments, you can use grams and it will all work out in the end. So I'm going to use grams because that's what 70–80% of students in the real Leaving Cert actually do anyway. So let's read through the question. In an experiment to determine the specific latent heat of fusion of ice, so it's the melting ice experiment, a student first crushed some ice. She then dried the melting ice. They're all words we've looked at already, before adding it to warm water in an insulated copper calorimeter. The following data was recorded. Now at this stage I like to do a little bit of working out. We're given the mass of the calorimeter and the mass of calorimeter plus water. So by subtraction there we should be able to work out the mass of the water used. We're also given the mass of the calorimeter and warm water after adding ice, so that includes the melting ice. So from this value and this value here, using these values, if we subtract them, we should end up with the mass of the ice used. That's 2 important values, and that's all the mass values we actually need in our equation. Then let's look at temperature changes. Well, we have the initial temperature of the water there, and the final temperature of the water there. So by subtraction there, we can work out the change in temperature of the water, which of course should be equal to change in temperature of the calorimeter. They should be equal to each other. And the only other thing we need there is the change in temperature of the ice. Now, we are not, as far as I can see, given any information about the initial temperature of the ice, but up there we were told that the ice was melting, so we can assume it's at 0 degrees Celsius. If everything then ends up at 8 degrees Celsius, the difference between 8 and 0 is clearly 8, so the change in temperature of the ice would be 0 degrees Celsius. We are also given at the bottom of the question the specific capacity of water as 4,180 joules per kilogram per degree and the specific capacity of copper as 390 joules per kilogram per degree. We now have all our information to throw into our formula to work out our value for specific latent heat diffusion of ice. And here are my calculations. As I showed you earlier, by subtraction from the data, I got the mass of the water, the mass of the ice. I got the change in temperature of the water, which will always be equal to the change in temperature of the calorimeter. And assuming the ice was melting, or being told the ice was melting, and assuming its value then, its temperature was 0 degrees Celsius, I worked out the change in temperature of the ice. Next step, we write down our formula that we have seen earlier. There is our formula. And we can put all these values into it. Putting all the values in, keeping in grams. It's so important to write your formula first, then substitute in your values without doing any mathematics whatsoever, and then in your third line start doing your mathematics. The good news is that in an honours Leaving Cert Physics paper at this stage you will have achieved most of your marks, and the marks for the mathematics are not huge. And I leave the maths to you, and I worked out with a final answer of 325,121.8 joules per kilogram. It's very important to know the correct units for this. Now moving back to the rest of the question. I don't want to keep you too long, so we'll move through it fairly quickly. You can stop the video anytime you want. The questions were asked, why did the student crush the ice? And the answer is to give it a larger surface area so it will melt faster. Faster is the most important word in that sentence there, that answer. Why dry the ice? Why was the ice dry? Why was there no layer of water around the ice? Well, so that only ice will be added to the calorimeter. Why? Wet ice has a layer of water around it. It already has changed state, so it has gained latent heat. It cannot gain latent heat again. Why was the ice crushed? Well, how was the ice crushed? Well, any reasonable method of crushing the ice would be accepted here. Use a hammer or any other method like that. How was the ice dried? Very simple. You use a towel, you use tissue paper, you use something like that. Why did we use warm water? And a lot of students will just stop after the first 4 words here, so the ice will melt. But ice will melt in cold water, but it would take a longer time. So why warm water was used? So the ice will melt faster. Faster is the important word in that answer there. Why did the student use melting ice? That is very simple. Melting ice is at 0 degrees Celsius by definition, and we need to know the temperature of the ice. And the last part there was, why could using a very large mass of water lead to a less accurate result? Well, if you used a very large mass of water, then and using the same amount of ice, the change in temperature of the water would be quite small. Small values put into formulas tend to lead to large percentage errors, so this could result in a smaller change in temperature of the water, smaller delta theta water, which leads to greater percentage errors, and that's the important part there. Now, was there anything else in that question? I think we're coming to the end of it. Okay, there are my calculations, and I think at the end there was oh no, there wasn't. I went on then to 2008. What I will do is, if I have this question done, I will just show it at the end of the video. Perhaps I haven't actually, I have. This is the 2008 question. I won't read through it. You just read through it if you wish and do it yourself, and here are my answers. Running through them pretty quickly there, but you can stop the video anytime you want. Thank you for paying attention.